Today, we'll talk about the very basic mechanisms of our planet's circulations. So, welcome everyone. Let's begin with a simple observation. Imagine you are heating water in a container over a low flame that's not enough to boil it. What do you think happens to the water inside the container? Would you notice any movement of the water particles? Let's explore what happens. As the water closest to the flame heats up, it makes water less dense. So the warm and lighter water masses, shown by bright red color, is now surrounded by cool and dense fluid mass. The surrounding denser fluid exerts a pushing force upwards on the lighter, warmer waters. This creates a flow within the container. Warm water rises as cooler water tries occupying the bottom space. The warm, less dense fluid rises to the surface. As it reaches the top, it loses heat to the atmosphere, resulting in cooling down and becoming denser. This cooler water then sinks back down towards the heat source shown by black arrows. Now, what drives this continuous circulation? It's the transfer of thermal energy. The heat gained at the bottom by the water closest to the flame drives the movement. As this warm water cools at the surface, it releases the heat energy back into the atmosphere. This cycle of heating, rising, cooling, and sinking creates a continuous circulation. Here's an interesting thought. Now imagine we completely change things up. Instead of heating the water from below, what if the heat source was located at the top of the container? What do you think would happen to the circulation? This time, the situation is reversed. The heat source is at the top and the denser, colder fluid is located at the bottom. What would happen in a setup like this? You may please pause the video if you need some time to think. In this scenario, you likely wouldn't observe any circulation. This is because the warmer, lighter fluid always remains at the top. However, the water would likely heat up much more slowly, with the warmth gradually transferring from the topmost layer to layers beneath. Now, here we have a new scenario. Imagine we place some ice cubes on the circumference of the container as shown. With this new setup, do you think there will be any circulation? Why or why not? Please take a moment to think about it and maybe pause the video if you want. I hope that you got that right. The resulting circulation pattern is indeed similar to the first case as shown. Here is why. The ice cubes cool the water particles closest to them, making them denser and causing them to sink down. Meanwhile, the heat source at the top warms the water particles there, making them less dense, causing them to spread out and replace the sinking water at the circumference. This creates a continuous loop. Cool water sinks, warm water spreads out, the cycle repeats. This circulation pattern is driven by sinking of denser cold waters. However, in the first case, if you remember, it was the rising of lighter warm waters. This experiment actually mimics a large-scale circulation pattern in the ocean. For us, sun is our source of heat. Energy-packed solar radiation warms the equatorial regions. Similar to the ice cubes in the experiment, we have polar ice caps, the Antarctic and the Greenland ice sheets. Now, why do we have polar ice caps? There's three main reasons to it. First, relative angle of sun rays. The sun rays hit the equator more directly, but sun rays spreads out as we move away from the equator due to the change in angle. This means poles receive less concentrated solar radiation. Second, seasonal sunlight. The poles also experience periods of extended darkness during winter months. This also contributes to the overall colder climate there. Third, high reflectivity. The ice sheets are highly reflective, meaning they bounce a significant portion of sun's radiation back into space instead of absorbing it as heat. This reflective property is known as albedo. All these combined, we have a cold and icy polar climate. As we discussed, polar ice caps play a significant role in regulating our planet's temperature. Let's get even more creative here. Imagine we have another container stacked on top of the previous setup. With this new configuration, what kind of circulation pattern do you think we might observe? Can you guess what might happen to the overall circulation? Well, it's time to pause the video and think. I'm sure you got this right. Well done. The warmer water rises and the cooler water sinks. This one is the very first case that we have discussed. Now, let's take this a step further. Just imagine that the bottom container acts as the ocean and the top container is a representation of the atmosphere. Now, what we have is a simplified model of our planet's atmosphere and oceans. However, the atmospheric circulation is not really accurate. Now, this one is a better representation of the atmospheric circulation. In the place of a single circulation cell, we have 3 cells in one hemisphere. The Coriolis effect plays a role in this. We do not have time to discuss Coriolis effect in detail here. However, in general, Coriolis effect can be explained by deflections observed in the trajectory of freely moving objects with respect to the ground below. In the northern hemisphere, these deflections are towards the right of the object's path, while in the southern hemisphere, they deflect towards the left. For example, the dashed arrows show the expected path of a moving object, while the solid arrows show the actual path. In this figure, we use additional arrows to depict east-west components of circulation. The arrowheads indicate eastward movement, while the tails denote westward movement. Now, imagine warm air rising at the equator. As it travels towards the poles, the Coriolis effect deflects it to its right in the northern hemisphere and to its left in the southern hemisphere. This deflection becomes more pronounced with higher wind speeds. Additionally, as the air moves away from the equator, it cools down rapidly at higher altitudes. However, the ocean beneath remains relatively warm. This temperature difference creates a density contrast. These combined factors contribute to the breaking down of a single circulation cell into multiple circulation cells. Since there is only 3 such cells in one hemisphere, we have names for all of them as shown in the figure on the right hand side. Just for your information, unlike our planet, a larger planet like Jupiter, which also spins much faster than Earth, experiences a more pronounced Coriolis effect. This combined with other factors leads to the formation of a greater number of cells as opposed to Earth. The Coriolis effect, as we have seen, introduces east-west components to the circulation between the equator and the poles. At the surface, as illustrated in the figure, in the tropics, this translates to easterly winds or trade winds. In the mid-latitudes or within the Ferrel cell, we have westerly winds. What we have here is a toy model of our planetary circulation. It is a good idea to take a moment, pause the video, and let everything sink in. Now, let's go back to the oceans. The easterlies and the westerlies at the surface of the ocean can also drive ocean currents. These wind-driven currents, generally faster than density-driven currents, also deflect due to the Coriolis effect. In the tropics, easterlies drive surface currents westward. The Coriolis effect then deflects these westward currents poleward. Conversely, in the mid-latitudes, westerly winds drive surface currents eastward. The Coriolis effect then deflects these currents equatorward. These deflections contribute to the creation of large-scale circulation patterns in the ocean surface. The resulting wind-driven ocean circulation is shown by transparent arrows. Here in this figure, you can see the surface components of the wind-driven ocean circulations. The goal of this video is to explore how the temperature difference between the tropics and the poles drive circulations in the atmosphere and in the ocean. While you can find more information about these circulations elsewhere, let's revisit 2 basic experiments that we have discussed. From these 2 experiments, I hope you understand the significance of Antarctic ice sheets and the Arctic ice caps in our climate system. As the polar ice cover declines due to global warming, both atmospheric and ocean circulation get affected, and hence the entire climate system. Thank you for your time, and I really hope you learned something new or got a new perspective. Thank you.